So, have you ever looked at a magnifying glass or even just thought about how your own eye works and wondered, how does a simple curve in a piece of glass take all this scattered light and just magically focus it into a perfectly sharp image? Well, today we are going to pull back the curtain and uncover the exact mathematical formula that makes all of that possible. It really all boils down to one fundamental principle of physics. And we're not just going to throw the formula at you today. No, we are going to build it from the ground up, piece by piece, so you'll see exactly where it comes from and really get how it works. Okay, first things first. Let's imagine a single ray of light, just zipping along through the air. What happens when it suddenly hits, say, a curved piece of glass? Well, it doesn't just keep going straight. It bends. It changes direction. And that little bend, that is the core concept for everything we're talking about today. It's called refraction. Now, to build our formula, we've got to understand the blueprint, right? So I want you to think of this diagram as our cast of characters. Every single line, every letter you see here is a key player in the story of how light bends. I know, this probably looks a little intense, like something straight out of a heavy physics textbook. But don't worry, all the magic is happening right here. We've got our object, we've got the curved surface, and we've got the image that's formed. Let's just break down each part one by one. So, first up is this letter N, which stands for the refractive index. The easiest way to think about this is as a material's light-bending power. Something with a high N value, like glass or water, is really good at slowing down and bending light. Air, on the other hand, has a really low N. In our setup, light starts in one material, which we call N1, and then enters the second material, N2. Simple as that.
And this straight line cutting through the middle, that's our principal axis. It's basically our main line of reference, kind of like the equator on a map. Everything we measure is going to be relative to this line, and that central point M, which we call the pole.
Okay, so the whole game here is to figure this out. If we put our object O at a specific spot, where exactly is the image I going to show up? To do that, we have to track two really important distances. U, which is the distance from the surface to the object, and V, the distance from the surface to the image.
And what about R? Well, the radius R just tells us how curvy our surface is. A really small r means you've got a super curved, powerful surface that bends light like crazy. A really large r means it's much flatter, more gentle. And this value, it is absolutely essential for our final formula.
All right, we've met all the key players. Now for the fun part. It's time to see how they all interact. We're going to mix a little bit of high school geometry with one major law of physics, and we're going to cook up our final formula. We're going to tackle this step by step. See, we start with some pure geometry. Then we bring in a law from physics, use a really clever math trick to make our lives easier, and boom, we land at our final equation. It's a really beautiful, logical path. We kick things off with some simple geometry. And hey, don't worry, you don't need to memorize these formulas on the screen. The main idea here is that we can use a basic rule about the angles in a triangle to describe our two most important angles. I, the angle of incidence, and R, the angle of refraction. Okay, now we bring in the physics. Snell's law is the big rule that connects our angles to the bending power of the materials, but you can see it has those sine functions in it, which can make the math a little messy. So physicists use this awesome shortcut called the small angle approximation. The idea is that for light rays that are really, really close to that central axis, the angles are so tiny that we can pretty much just ignore the sine part. This cleans up the equation beautifully, leaving us with something much simpler, n1 times I equals n2 times r. And now for the final step, the grand reveal. We take those geometric expressions for our angles, we plug them into our simplified Snell's law, we do a little bit of algebra, and we arrive here. This is it, the single elegant equation that connects everything, the object distance, the image distance, the materials, and the curve of the surface. So we have this cool-looking formula, but does it actually work? I mean, an equation is only as good as its ability to predict what happens in the real world. Let's put it to the test. Okay, let's solve a light puzzle. Imagine a tiny point of light in the air. It's heading towards a curved glass surface. We know how bendy the glass is, we know exactly how curved the surface is, and we know how far away the light source is. The only thing we don't know is, where is that final image going to appear? No, hang on. Before we just start plugging in numbers, we have to follow one super important rule, the sign convention. Think of it like this. Light is traveling in one direction, let's say left to right. Any distance we measure with the flow of light is positive, but any distance we measure against the flow of light is negative. So since our object is to the left of the surface, we have to go against the light to get to it. So its distance u is negative 100. The center of the curve is to the right, in the direction of light, so its radius r is positive 20.
So we take all our values, we carefully plug them into our master formula, we solve for v, and we get our answer, positive 100 centimeters.
But what does that little plus sign actually tell us? Well, remember our rule. Positive means in the direction of the light. So this tells us the image isn't on the same side as the object at all. It actually forms 100 centimeters inside the glass, on the other side. See? Our formula didn't just spit out a number. It gave us a precise location. It works.
Okay, let's do a quick recap of what we've uncovered and talk about why this one seemingly simple formula is actually so incredibly powerful.
So what did we learn? At the end of the day, it comes down to one core formula and one crucial rule for science. And these two tools, they aren't just for solving problems in a textbook. They are the absolute foundation for designing and understanding every lens system you can possibly think of, from a simple magnifying glass all the way up to the complex optics in the Hubble Space Telescope.
Right, this formula cracked the code for one surface. But what happens when you add a second one right after it? Well, then you have a lens. And here's the really beautiful part. The image that's created by the first surface becomes the object for the second one. By using the same formula over and over, you can build everything from a camera lens to a microscope, a telescope, and even finally understand the amazing lens that's sitting inside your very own eye.